Our motto is, it's better to rise up than to be left below.
Is currently at a floor function. The floor is the least integer that is greater or equal to 1. For example, if x equals 1.130, then the floor is equal to 1. The domain is negative infinity to positive infinity. The range is y is an element of integers, and it has to be an integer, aka a whole number. The end behavior is x to negative infinity and x to positive infinity, and that's the same as y. This is what the floor function looks like. This is how you would plug it into a calculator.
Spread it across the country. Here we go back. This is the moment. Tonight is the night. We'll fight till it's over. So we put our hands up like the ceiling can't hold us. Like the ceiling can't hold us.
Truly is currently at a ceiling function. The ceiling is the greatest integer that is less than or equal to x. For example, if x equals 1.13, then the ceiling is equal to 2. The domain and range is the same as floor and ceiling. That wasn't English, but that's okay. The end behavior is also the same. This is what the ceiling function looks like, and this is how you plug it into a calculator.
This is what the parent floor function would look like when graphed. This is what the parent ceiling function would look like when graphed. Each of these graphs look like a staircase, except they're missing the vertical parts of the stairs. When a floor and ceiling function are graphed on the same graph, as so, the ceiling is directly above the floor. In the parent equation, when the coefficient of x increases, regardless of whether it is for the floor or a ceiling, the length of the line segments decrease, and the smaller the coefficient of x, the larger the line segments will be. Like we stated earlier, the domain for both floor and ceiling functions are negative infinity to positive infinity, and the range is y is an element of integers, basically saying that they must be whole numbers. The way to tell whether you are looking at a floor function or a ceiling function when looking at a table is by comparing the y values to the x values. For each x value, if the y value is smaller than the x value, then that means you are looking at a floor function. If for each x value, the y value is greater than the x value, then you are looking at a ceiling function. When looking at a floor function and a ceiling function on the same graph, it is much easier to distinguish which one is which, as the ceiling will always be directly above the floor, as long as the coefficients of x are the same for both. However, when looking at either a floor or a ceiling function, it's hard to tell which one is which. The way you can tell whether you are looking at a floor function or a ceiling function is by looking at the x and y values. For example, for a parent function, if one of the x values on your graph is 3.4 and the y value corresponding to it is 4, then you know you are looking at a ceiling function, since the y value is larger than the x value. Or, if one of the x values is 5.6 and your y value is 5, then you are looking at a floor function, since the y value is less than the x value. For a general rule of thumb, if a y value is less than the corresponding x value, then you're looking at a floor function. If the y value for a given x value is greater, then you are looking at a ceiling function. This function can be used for numerous real-life scenarios. For example, the ceiling function can be used to represent how much you pay for talking on a phone. For example, in this table, if you talk for more than 0 minutes but less than 0.5 minutes, you would pay $30. Then, if you talk for any amount of time over 0.5 minutes but under 1.9 minutes, your price to pay would jump to $50. If you talk For any amount above 1.9 minutes, but below 2.56 minutes, your price would jump to $65, and so on.
To make vertical lines using floor and ceiling functions, you just simply have to switch the x and y. So instead of y equals floor of x, you would put x equals floor of y, and vice versa with ceiling. You can make a lot of crazy designs with floor and ceiling functions. For example, the first graph you will see is made up of vertical and horizontal floor and ceiling functions. I made this design by first plotting the parent functions of both floor and ceiling, and then added 1 to the end of each, and then 2 to the end, and so on. The second graph is made up of diagonal, floor, and ceiling functions. The equations for this graph are a little strange. I used the basic equation of 1y equals x minus floor of x, and 1y equals x minus ceil of x. To make the various lengths to the diagonals, I multiplied the y by different values.
Chasing waterfalls, please stick to